Okay. Hello. Yeah. Thank you, Mark, for your very kind introduction and kind invitations. So my name is Hoa Bui, and I'm from Curtin University, especially from the AIC Training Center for Transforming Methods through Data Science. So the talk today is about one of our work on the method scheduling in chemical processing plants. So in a mining industry, especially in chemical processing plant or refineries, then every access experience some form of degradations. And so maintenance access is a crucial business function with a massive impact on productivity, environmental impact, and safety. And the maintenance take up to 30% and 50% of the company annual operating budgets. So this is, and especially for chemical processing plants, the shutdown maintenance is one of the most critical maintenance activity. So shutdown means you have to turn off the asset, take it out of production, and before maintenance activities. The reason for that is because during the production, the assets have a high pressure, high temperature, and the chemical is very dangerous. And for that reason, shutdown maintenance have a direct impact to production because the access is out of productions. So the production for the site will reduce. And also shutdown maintenance have a indirect impact to production, because if you don't have a effective maintenance, then it's highly likely that you can experience a breakdown, which will affect the production, and also the cost for maintenance is going to be 3 times higher than planned maintenance. So for shutdown maintenance involve a massive planning, because because it have direct impact to productions. That is why you have to not only plan the maintenance, you have to plan the production and plan the resources and inventory management. And when you plan all of the shutdown, then you have to take in account to equipment, parts, personnel, contractors, and many other factors. Because nowadays we experience a shortage in resources, especially skilled workers, and the international competitions, then the budget for maintenance is a prime target for budget cut. So that is why scheduling and planning for a shutdown is very important to have a effective maintenance, and also to reduce the maintenance cost and reduce the downtimes, and also to minimize the risk. But nowadays, but now in mining industry, maintenance scheduling usually all manual, and which by nature is ineffective, and which characterized by, for example, ineffective use of resources, or increased inventory, or inflated cost. And all of the tool we are using right now is like a SAP, Microsoft Project, or P6 is only about visualization or analytic tool, or management tool. It doesn't have a built-in optimization functionality that can inform or help the manager and scheduler to make to optimize their schedule. So that is why. We have a team we just a part of the ITTC Center from Curtin University, and collaborate with several industry partners to put the goal to optimize, to develop some tools so that we can incorporate the optimization into the planning and scheduling in mining, for maintenance for mining industry, and for our industry partners. So in the talk today, I'm going to talk about the mathematical side of the shutdown scheduling tool that we developed. To have a tool for industry to use, we not only develop the optimization model, or mathematical foundation for it, we have to develop other functionality like visualizer or comparison tool, but we're not going to focus on that. So the outline of the talk is we're going to talk about the medium-term shutdown plannings, and with focus on problem description, solution approach, and broader, we're going to explore the binary non-convex quadratic programming current stage, and this is our new approach, and we present some numerical results. So we don't have numerical result for industry side. We couldn't present that, but we present the numerical result that we have a publishing our paper. So for shutdown planning, they have a different level. So whether it's a long-term planning, medium-term planning, and detailed planning, where you actually decide, okay, which job start at what time, execute by which crew. So the talk today is focused on the medium term. Is about we plan ahead what activity in say 12 weeks or 6 months ahead, which asset to be maintained during this period on what days. The reason for this is that because we maintain asset, we have to turn it off, it affects the production, and then we have to minimize the impact of the maintenance activity on production. So so if we look at the whole site, we have a set of assets that need to be maintained. So the maintenance activities is whether preventive maintenance, it's like you have a car and then you're gonna maintain it for every 6 months, or corrective maintenance, like through inspection or prediction, the assets likely to fail in 3 months, and then you have to do corrective maintenance before that to avoid breakdown. And each asset have a maintenance time windows and maintenance durations. And for the chemical processing side, it is more complicated because the assets here are interconnected. So when assets are interconnected, then when you turn off the asset, it's going to create maintenance clash. So what I mean by maintenance clash is that, for example, 2 assets is turned off or down as the same days, it will create some clash. So it's either 0 clash, means that it doesn't create any impact, or it's create positive impact or negative impact or alignment. So as an example, what is negative alignments that could have? So if 2 assets turn off at the same time, it will create negative impact, whether it's production lost, a safety issue, or environmental impacts. For example, you have a stream of chemical go through here, and you have 3 vessels, and then each vessel gonna share a lot of 60% of the stream. But now when you take one vessel out, two vessels can carry that flow. But if you turn off 2 vessels and only 1 vessel left in the production, it's not only affect the production because we cannot control the flow, but also create environmental impact and safety because the likelihood of that, the third one to be breakdown is very high. Or positive alignments, like when 2 assets turn up at the same time, this will minimize the total downtime and hence minimize production lost. Like for example, for some asset, when you turn off that asset in that area, you have to turn off all the assets around that in that area, which means that not only one asset is turned off, the surrounding assets are turned off as well. So this is actually the opportunity to perform extra maintenance activity for other assets have been turned off. So if we can align the maintenance activity at the same days, we can minimize the total downtime for all of these assets and hence minimize the production loss. So these two are just only 2 examples how the asset interconnected asset can doing the maintenance can affect the production. And of course, like any other organizations, we have a resource limit. And the 5th one is each maintenance work orders has a priority, like because some activity is more important than another. and have multiple sub-activities as well. So what I meant by that, because for example, when you want to maintain your car, so your car is the purpose, the maintenance work order, but there are many sub-activities like to drive the car to the workshop, the mechanic open the car, or maybe the electrician test the electricity, and then the cleaner do the jobs, and then some other activity as well. So it's not the case that for the whole duration, say 12 weeks, you need one cleaner for the whole duration. No, you probably need one cleaner after 5 days when you turn off the asset. So they consist of multiple activities and must be done by the right sequence. So this is the problem description. So the optimization model is rather simple. So we only need to decide which order to the start days of the work orders. And then we have to take care of the duration, the due time, the resource limit, and to maximize the positive alignments or minimize the negative alignments. So to simplify the mathematical formulation, the decision is binary. We just take value 1 if the maintenance for asset I start on or earlier than that day D, and similar thing to the finish day. And then the difference between them is 1 if the asset is turned off on that day's D, and then the input we're considering is the job durations, the time windows. Like row I means is the earliest day that the maintenance work I can start, and row max I is the latest day that the maintenance I can start. So some maintenance work doesn't have that time windows, but most of the case has. And also the resource uses for the maintenance activity and the daily the capacity of the whole mining site. Then the constraints are simple as well. We have cumulative property that if the job I has start before day D, then of course it has start on day D plus 1. Same for Z. And then the access, the maintenance work I cannot finish before it start. And the durations, this means that this one means the right-hand side formulations mean that it cannot finish if the days is less than the duration of the activity. And the left-hand side is so when xid equal 0, which means that it hasn't started yet, then after delta I day, it hasn't been finished yet. And if xid equal 1, which means that it is finished before day D, then after delta, it has started before day D. Then after delta I days, it has been finished, which means that zid plus delta I equals 0. And some windows also straightforward. Well, so the start days is 0 if the days is earlier than the compulsory days, earlier than the earliest day that the maintenance work can start, and it has been started if the date is beyond that time windows. And the result limit is a little bit complicated. If at any days that the maintenance I require exactly that amount of resources of type M, then we have this resource capacity. But as I explained before, it's not the case because maybe it's only require one cleaner on the first day or on the last day, and that's it. So we have to take care of the sub-activities. So let SI is a set of activities that within the work orders. So for example, this one is electrician, like boiler maker, mechanic, and fitter, for example. Then for each activity S, it has a duration delta S. An activity defined sequence is defined on how many days this activity had to start when the work order started. So for the activity S here, it must start delta S day when the work order started. So this one is delta S, small delta S. This one is big delta S. So if we define the sequence like this, then we replace the resource constraints on a activity level. So first we have to redefine the start dates of this activity based on X. So Xi is the start dates of the activity of the work order I. Then when the work order I start on day D, then the activity S start on day D plus delta S. So which means that this X here, receive value is 0 or 1, it depends on X D minus delta S. So we do the same thing. We redefine the finish date of that activity S, similar to here, that we take this one is the finish date of the activity S, and then we shift this day from, this is Z I, we shift ZID forward to this one. That's why we have the minus this one here. So this one is delta I minus delta S minus the big delta S. And then we do simple resource constraints on activities level. And then now measuring classes. So ideally bad alignment shouldn't happen, but sometimes unavoidable. The reason for that is that because of the time windows. If we have so tight time windows, then at some point we cannot avoid the clashes. So we only can minimize the number of days that we have clashes. And good alignments are desirable, but sometimes impossible. So the reason for that is also the time windows, because if the two activities have like no clash time windows, then we cannot have the good alignment happens. More importantly, good alignments cannot happen because of resource limitation, because we cannot do every activities as one. So that is why we only can minimize the impact, minimize the clashes. So the clash matrix is given by the site. It's given by the site. It defines whether two axes is turn off at the same time if we create how much impact to the productions or the safety. So if it is positive, then it is positive alignments. If have a negative value, then it is a negative alignments. And with 0 means that it's independent, that you can turn it off at any time and it doesn't affect anything. So now we have to maximize the total alignment of the maintenance activity. So the clash happen only when two maintenance work start on the same days. No, sorry, happen on the same days. So this one equal 1 if maintenance I is active on day D. So this one equal 1 if maintenance J active on day D. Then the multiplication of them equal 1 only if they are active on the same days. And then it's multiplied with the value of the clash, and we try to maximize it. So now everyone, probably from the beginning, everyone have that feeling that, well, we have the quadratic problem here, but now this is clearly that we have the quadratic objective. So the preliminary models look like this. This is a binary but there are a little bit complication into that because the resource capacity is very tight. So sometimes it's impossible to schedule on the work orders in the right time windows. So some activities we impose the penalty function to allow the overrun or advancing the maintenance I, so that to respect the resource capacity. And then we just penalize on any days that this maintenance start beyond the right time windows. So preferably we have to start in the right time windows here where we don't have any penalty. But if we decided to start advancing the maintenance, then you receive a penalty, and it's gone. The further you delayed it, advancing it, then the higher penalty you receive, similar to the delaying the maintenance. So you can choose this function as not piecewise linear. So we have the functions fd, and this is the penalty functions. So if you can see here that objective is to minimize the penalty function fd, but this is not a linear function. So we need to linearize it. So So if we define theta I as a continuous variable defined for the penalty for advancing and delaying dimension I, then we will replace the objective function f by the following three constraints. So basically it's saying that, okay, keep in mind that xij minus xij minus 1 equal 1, if and only if dimension I start exactly on day t. This is the days when it transforms 0 to 1. And the first constraint said that, okay, the value theta I had to stay below 0. And then if d less than the minimum days, rho mean I, which is this day, then it will then the value of the function on the second constraint, on the left hand side, going to receive a positive value, and exactly this value. And then theta I had to stay below this stay above this red line. And for the third constraint, because when third constraint, now if d is less than, stay this side, which means that it's less than rho means I, then the value of the function here on the third constraint gonna be negative. So that's why that constraint becomes redundant. Similar things for d bigger than rho I max, then the third constraint will be active and the second constraint will be redundant. And when rho equals it. So the more importantly that how we deal with quadratic objective, because on the paper number 1 here, so this is more or less a survey paper on the computational study on the non-convex cardinality quadratic programming, where they compare the computational study of different solver for quadratic programming like Simplex or Groovy. And the survey said that even for a very simple quadratic programming like binary, non-convex, and with the dimension around 100 or 150, the Simplex or Groovy couldn't solve that instant, let alone like industrial size problem. And this problem is very simple with only one quadratic objective with one cardinality constraint. So that is why we need to try different approach to tackle the quadratic objective. The first approach is a standard linearization. This is when we usually start to deal with quadratic component. So for each pair I and j, we define a binary variables wij, just to define whether the pair I and j is clash on day d or not. If it is 1, which means that the pair I and j clash on day d. If it's 0, means that the pair is not clash on day d. And then we only need to update the objective functions like this, and then we rewrite the constraints so that wijd receive the value like we want. So the first two constraints to ensure that ijd will receive value 0 when none of the job I or one of the job I and j is not active on day d, which means that the right hand side here is 0. And the third constraint to ensure that when both job I and j are active, which means that both of them is 1, then the right hand side here is 1, then wijd had to receive value 1. So this is so we have a linear model in replace the quadratic model. But the problem with this one is that the decision variable grow quadratically, because now we add the variable wijd. So the dimension of wijd is equal to the number of work order, like square, and multiply the number of days. So it's quite substantially large. So yeah, so that's why we do a second approach, which is used based on the Glover linearizations. So you can see there's a reference here. So the idea of this linearization is that instead of consider which pair active at what time, we gonna for any days we kind of calculate the alignment value that one particular maintenance I can create on a day. So for example, if a job I is not active on day D, then theta is 0. But if the job I, the maintenance I is active, then theta I is gonna be receive the value of all the other axes that be on that days and create whether negative or positive impact on that kind of summation all of them. So if we add this decision variable, then what happens? Then we update the objective like this. So the object, so we have to divide by 2 because if we count the value for maintenance I, then probably we have to count double time for another maintenance J because I and J together create that alignment value. And so our goal first is that when I is not active, then it must receive value 0. Then the idea is to use big M constraint. So what UI is an upper bound for theta IG. So when this one is 1 is 0, which means that the right hand side is 0, then theta ID must equal 0. But when xid, when the job I is active on day D, then the second constraint is redundant, but then the first constraint become active because this side, the first value here, UI here is 0, and then theta ID receive exactly the value that we want, which is collecting all of the clash value that for all the job I that are also active on day D. So now we only need to maximize that value. So now the number of decision variable now reduced to not the square of number of work orders, but like 2 times. But note, we have to be careful when you choose UI because it shouldn't be too large because it will affect the linear relaxation for branch and cut algorithms. So you can find that comment here. Well, but even if we do the global linearization like this, the computationally is not improved significantly because it still suffer for even quadratic knapsack problem. It would still suffer of dimension 200, and it's not a dimension that we want. But that is why we're thinking about the third approach, which is cutting plane methods. The cutting plane method is not new. It is just similar to outer approximation, or even bending decomposition is some form of cutting plane algorithm. So, so what is the basic methodology behind the cutting plane methods for quadratic function, quadratic problem? So, for example, you have a quadratic problem QP with a quadratic objective, and subject to the constraint set K, x belongs to K. So K can be a binary solution. A binary is a constraint set. It can be binary variables. And then we put the quadratic term from the objective function into the constraint and replace it by the value theta. So theta is the variable represent the value of fx. Then we maximize theta, and we have to constrain theta as a true value of the function f. Sorry, the quadratic term. So we book that into the constraint, and then we use the linear approximation. So note that if the Q is the negative semi-definite matrix, then the function is a concave function. Then the function is the lower envelope upon the tangent plane of the functions at the considering point K. So basically, we can replace the right-hand side here by the infimum on of the cutting plane So, and then when we receive replaced by infimum, sorry, supremum, then we can write them as a linear constraint like that. And this linear constraints hold for every k y belong to k. So basically, this one is the upper plane or the tangent plane of the quadratic function at each point y belong to k. However, it is impossible to generate all of the constraints in start. So we have to generate them gradually. So now it's similar to Benedict decompositions. So instead of, or maybe lazy constraints. So we only add the constraints when we found that our solution is active. We add that, so we check whether our solution, our candidate solution is actually active or not, is actually optimal solution or not. So this one is so which means that if we take we start with just one constraint or no constraint at all, and then we add first starting so x naught is actually represent one cutting plane, because from one point we can generate one cutting plane, and then we start with one cutting plane, and then we find a feasible solution so that we have an improved solution. So these conditions mean that our that we find a solution which is active, and then we will add a cutting plane. We will update the lower bound, and then we update the cutting plane to check whether this constraint at xk is active. So we have to add that constraint to check that whether xk is optimal or not. So if we cannot find the optimal any more improved solution, then it's going to be then we found the optimal solution. But this with that condition is maybe weak. So we can incorporate with the branch and cut algorithm, because we can make use of the upper bound for the linear relaxation for the problem, so that we can create a new another stopping conditions compared with lower bound LPK. So for that one, we can introduce a new auxiliary variable, which is theta d, which is the over values, clash values obtained on a particular day d. And then we maximize it, and then we add cutting plane. The number of decision variable reduced to just the number of days, but to this one. But the problem of this one, there are a couple of problems. This one, the first problem is that, because remember that we need the approximation to support the cutting plane to work. In other words, that the matrix Q must be negative semi-definite. But in reality, we don't have that nice property. So the cutting plane does not necessarily convert an optimal solution. So outer approximation or cutting plane methods, do we really need concavity? Because for outer approximation philosophy, we first represent the convex constraints or nonlinear element by an intersection of half space or by a collection of linear elements. And if that approximation is precise, then we have an exact algorithm. But cutting plane actually different. So cutting plane is that we add the cutting plane to tighten the set in such a way that when we add enough cutting plane, then the optimal solution is found. Then we don't actually need the concavity to ensure the exact approximation. We just need to somehow certify this condition. So what is exactly these conditions? So this condition is about each cutting plane you add, you must remove at least one new feasible solution. Otherwise, you can create the loops. For this condition, it's to ensure that the algorithm gonna converge finitely, because we have a finite finite domain. And the second condition is that each cutting plane must not remove optimal solutions. So which means that when you add a cut, the optimal solution remain in the feasible region. So when the algorithm terminates, then the optimal solution is tractable. So So for the cutting plane methods, we can actually respect this. And then we will have a convergent to optimal solution. But if we rewrite that idea mathematically, it's going to be like the optimal solution, so that it satisfies every cutting plane. Well, but this condition is not tractable. The reason is that we want to find X star, so we cannot use X star to check. Then we have some other, conditions to check. Like for example, Q is negative semi-definite, of course, or Q is a positive matrix, but at most one positive eigenvalues, or Q is a conditionally negative definite. So conditionally negative definite means that, so the proof can found here. So the conditional negative definite means that the function, the quadratic term here is less than 0 when X lie on this hyperplane, and the constraint sets contain the cardinality constraint here. So these are on the special cases. We have some other special cases as well, like quasi-convexity, but we're not going deep into that. So even if we cannot do anything better, then we have to go back to the idea of outer approximation to convexify the problem, which means that to change the problem into the form that we are comfortable. So the convexification is when we transform the problem QP into this form. So keep in mind that because we have a binary problem, which means that xi equal xi squared. So the idea is that when we change the diagonal of Q by minus a rho, we minus the diagonal of Q by a parameter rho. So which means that the quadratic term gonna add rho xi squared, a half, of course. Because of that property of the binary problem, when you minus the rho I squared, a half rho I squared, then you add the linear term here, then this problem QP rho is actually equivalent to the problem QP. But what is interesting, what is new, better for this formulation is that when rho is bigger than the largest eigenvalue of Q, then the new matrix here, when we subtract all of the rho here, gonna have all of the new eigenvalue of that matrix is always negative, which means that we transform Q from normal matrix into a negative semi-definite matrix. So now the function become a concave functions. But this approach is actually not new. This is actually adapted into simplex here. So you can find a computational study here. But for this problem, for this approach, it seems too good to be true, because now you can work with any quadratic problem. You don't only to manipulate the diagonal of the matrix. But it turned out that this approach computationally even worse than a standard linearizations on average. So it seemed not good. What happened? So we suspect that the reason behind that, because we manipulate the matrix too much, we subtract the maximum eigenvalue of the matrix is actually a big step. It completely changed the structure of the problem. And it's not to be true, because if we consider, so actually this one also provable. Oh, sorry. Yeah, it's also in the manuscript that suppose we have two parameters, rho 1 and rho 2, with rho 1 bigger than rho 2, and then we consider two constraints, 1 and 2. So actually the constraint 1 is the cutting plane generated for problem QP rho 1, and the constraint 2 is a cutting plane generated for the problem QP rho 2. And what happened is that when constraint 2, when rho 2 is smaller than rho 1, then constraint 2 implies constraint 1, which means that the constraint 2 is stronger than constraint 1. So the constraint 2 rule out more non-optimal solution than constraint 1. In other words, the cutting plan generated for problem QP draw 2 is stronger than the cutting plan generated for problem QP draw 1. So now we question back about the way we convexify, that whether we should convexify choose such a large parameter, the largest eigenvalue of the matrix Q. Probably not, and probably that's the reason why since blacks perform computationally bad with the cutting plan algorithm. So how do we choose parameter rho? So we have two scenarios. The first scenario is that when the matrix Q is not negative semi-definite, then we should choose a suitable value Q rho so that we achieve the conversion to optimal solutions of the cutting plan. But when the matrix Q is negative semi-definite, then we can theoretically apply the cutting plan directly and it converts. But we should choose a negative value rho so that we obtain even a tighter cut for the cutting plan. Yeah, but it's nice to know, but how do we do that? I think we need to explore the structure of the problem. For example, if we consider the following binary quadratic problem like this, then with a special structure on K, which is a equality constraint, then if even data that V is the eigenvectors corresponding to the largest eigenvalue of Q, then we can choose rho as the second largest eigenvalue of Q. So we used min-max theorem to prove it because the function here So now this is a numerical result on one of the problem, just to demonstrate how choosing rho is actually impact the cutting plan algorithm. So it's a numerical result for the p-dispersion-sum problems. So if the matrix, so this is a problem of locating. So you have n different points, and then you have to choose p. You have to choose the location for p point, so that the total distance, the summation of total distance is the largest one. Then the matrix Q is a Euclidean distance matrix of n point in the Euclidean space, and K contains cardinality constraint, which means that this is equal p, or summation of all of the selection is p. So this is a problem you can see found in reference 9. And in this case, we prove that we actually don't need convexification step, and we can choose rho equals 0. And then the performance of the cutting plan algorithm actually we can generate randomly, but we can use a test set here proposed recently as a new test set for p-dispersion-sum problems. Then interestingly, we have this is a numerical result for yes. So we set the time limit is for 10 seconds and 100 seconds, and then we solve and report the solution. So compare first with simplex. That okay. So for the instant with so simplex can solve on an instant of dimension 25 with no gap, and then there for dimension 50 to 2000, none of in 10 seconds. So none of the instant can be solved, and then this is the gap for simplex. For cutting plan, it can solve for 10 seconds. It can solve up to dimension 1000 all of the 20 instance with no gap, and for 2000 it can solve 18 instance. Well, this is a gap, but we allow for 100 seconds. Then the simplex perform a little bit better for dimension 50, but not very good for other, still not very good for other dimensions, higher dimensions, and the cutting plan can solve all of them. Oh, and the performance reviews paper can be found here. Yeah, so this one is another different. Okay, so this one is the is report on the number of cut added for each dimension, and dimension is n, and p is a number of location that we want to choose, and the number of cut that cutting plan that we have to add, and then the seconds that being solved. So we see here that this still within 20 seconds, can solve within 20 seconds. Well, that is just a part of the, this is a part of the picture, because even if we can solve the problem for 1000 2000 activities, so what? Because the dimension actually bigger than that. Actually, the dimension is higher than actual problem is much higher than that. So so for this particular problem, then the class matrix is actually spot, which means that the asset actually relate to each other within the location. So it's not, so when the process chemical go, so this asset turn off property doesn't affect the asset at the end of the chemical. So the class matrix actually look like this. So we should make use of it. So we can decompose the problem, the quadratic problem into different block matrix and solve the problem by block. But the problem here is that for the mining side, the resources are shared within all the location. So even if we solve them block by block, but the resources share. So we have the constraint connecting them. Each block so if we think about the decompositions for this constraint, I think the best to do is think about Lagrangian decompositions, because we only have one we have connecting constraints and capacity constraints. So if we think about if we have one particular resources of type M allocate to one block, then we can solve each of the block in parallel. So we can actually rewrite the problem into maximize of one function f b based on block with the value given ymdb, which is the resource allocation. What is the best possible with the optimal solution, optimal value of this model in red, given the resource allocation MDB, and then we have to make sure that this resource allocation respects the resource capacity of the whole site. And then we have the decomposed problem like this. So it looks very simple. And then we can have the Lagrangian relaxations. And for Lagrangian decomposition relaxation, for any lambda that's positive, then when we solve this problem versus L lambda, then we will have obtained a upper bound for the problem. Then naturally we're gonna have so we try to minimize that upper bound on the right hand side. Then we can obtain the tightest upper bound for problem B. For problem B. So, but the optimality gap is not zero, unfortunately. So we have to go from here is branch and probably use branch and bound. But this is a different story. So thank you very much for your attention.